you decide base speed? So basically, there are two angles of it. Base speed will be decided when you design the motors. Okay, so when you select your motor, number of slots, number of turns, all those things, motor dimension, from there you will going to get base speed. And how much base speed you need, that you can calculate based on vehicle data. But base speed will be determined from above base speed. Again, I'm saying above base speed, we are going to give ID negative. Below base speed, ID 0. Above base speed, ID we are going to give negative. Deep above base speed, ID is going to be more negative. Okay. So logically try to understand. ID negative means you are basically weakening the air gap flux. Sometimes it may interfere with your magnet and it may demagnetize the magnet. If you give too much negative current in the ID axis, it can demagnetize your magnet. So that is one of the problem with PMSM. You must have seen PMSM as a demagnetization problem. From where it comes? It actually comes from this negative ID business. Okay, so that's why in your controller you must be very careful. Limit your demagnetization up to a limit which your permanent magnet can withstand. Otherwise your PMSM may fail. Okay. Why aluminum winding bad? I never said it is bad. It is a comparison with respect to copper. Copper is better. That's what I said. Aluminum has more resistance. That means more losses as compared to copper. Okay, and aluminum is kind of brittle. It's not that flexible like copper. So when you do windings in the machine, it has to be very flexible, right? If it is very rigid or brittle, it will create a problem. So these are the two major reasons why aluminum is not preferred. In heavy electric vehicles, to provide the speed governor, it may be, I don't know whether it is a question or statement, but in most of the electric vehicles, the speed control is simply done by your motor controller. Alright, so with this, let us go for a break. What we are going to do after the break, we are going to talk about motor controller, some design step by step, what we typically do, and whatever questions is left from your side. And if time permits, we'll touch briefly upon the PLDC also, little bit, okay, maybe for 15-20 minutes. So let's go for a break and then we come back from here. So that you can go to the next part. Please type yes if you can see the slides. Okay, so let me begin. It is already, we need to wind up on some topics. Okay, so another quick question to resume. What type of switching devices to choose in this, right? So as I told earlier, we need to have fully controllable device. Okay, for example, MOSFET, IGBT, these are the most common choice, right? MOSFET typically will prefer if your battery voltage is typically less than 100. Okay, IGBT you are going to use when your battery voltage is typically more than let's say 300. Okay, and in between we have to do a lot of loss analysis, cost analysis to find out the proper switching device, right? So you can see typically two-wheeler, three-wheeler which uses battery voltage of 48, 72 volt. These will be generally using MOSFET. And three-wheeler and the higher range four-wheelers, right? Typically they're using 350 volt, 400 volt, 800 volt batteries. So there typically you will see IGBT as most common choice. Okay, this all we discussed earlier also. So sometimes one of the device, any physical device, they have their own voltage and current limitations. Okay. Typically, sometimes you will see that we connect several switches in parallel. Okay, for example, this is one leg of the device, right? Let me call it S1 and S4. In case we need higher current rated device, sometimes what we do, instead of one device, we connect multiple devices in parallel. This is quite common in EVs. Okay. So what is basically happening? This is S1, this is S4, but effectively in S1, 4 devices are in parallel. Why we do that? We mostly do it to increase current rating. So for example, sometimes you may see that you need a, let's say 300 ampere current rating. How to do the current rating calculation? You already did it earlier. And the device you have in your hand, let's say it is a 100 ampere device. So you need 300 ampere, you have 100 ampere. So what you have to do? You connect multiple devices in parallel. Okay, parallel connections makes your current rating higher. This I'll skip. So for rest of the time, let me discuss about typically, what are the design steps that we use to finally get this motor controller hardware or final version done? Okay. So first, stepwise, we start with define system requirement. Anything you want to design with, right? You need to first get a clarity of what you want and what is required from that particular product. That requirement you have to understand correctly before you make it, right? So what is the requirement for our case? This is an example that I gave for a roto motor controller. That means that electric three-wheeler, right? So typically, we have to understand what is the voltage at the input that we need, right? For example, in electric rickshaw, we need a 48-volt battery. That's what we told multiple times. I showed you some images also. So that is one of your requirement, that my motor controller should be capable of handling around that voltage. If you are designing it for four-wheeler, you will be saying 350, 400, sometimes 800 volt, right? Then comes power rating. So what is the power rating that you need from the motor? Based on that, you have to calculate what is the power rating for motor controller. So just a reminder, last week, if I remember last week, I gave you homework, how to decide ratings of electric rickshaw motor speed, torque, etc. Right? I don't know how many of you did it. If you did it, you already know how we do these things, right? I did not receive any doubt from your end, so I understand that everyone has done it, right? Thank you very much for your kind support. So this was the homework that I gave in the last class, last week. So there I gave you some specification, and based on which you have to select motor ratings. So first thing is that from those requirements, you have to find out what is the motor that you're going to use, and at the input, what is the battery that you're going to use. So based on this, your motor controller specification will be decided, right? So motor rating you need to know. Similarly, from the torque rating of the motor, you have to find out how much current the motor controller has to deliver. So that will also go into that. Then what is your efficiency target? Typically, you want it to be at least 95% efficient, right? Then there will be some target that you want your motor controller to be within certain kg. You don't want to be heavyweight. And there will be some type of dimension restrictions. You have to design your entire system within this much size. Then comes the IP rating, right? IP rating is ingress protection. So you must have seen that when I showed you the image of e-rickshaw, the motor was exposed to the environment, right? Similarly, motor controller is also it is there in the vehicle. So these are all used for outdoor applications, isn't it? So this motor controller, they may subject to dust, it may subject to some water level issues, right? So how your motor controller or motor is protected from the water and dust, that the rating is given by ingress protection rating. Okay, for example, IP67. So this number 6 says it is dust proof, and this 7 indicates that it is a protection from water. So if you keep this motor below 1 meter water height for 30 minutes approximately, okay, and then you take it out, the motor, you should be able to run again. So and similarly, you may have IP66, IP65. For example, some it will be just protected from water splash. You cannot put the motor inside water, right? So different ratings, these are all standard information you will also get from internet in case anyone is interested. For example, I can show you IP ratings. I don't know whether it will open, but so this ingress protection rating, you can see there are some standard charts which will tell you which number is for what, right? So that you can study, and these are readily available. Sometimes it takes time to open, but this ingress protection ratings you can study, right? So there will be some electrical requirement, there will be some environmental requirement, right? All those things you need to write down from your requirement specification. That will help you to design your system as per requirement. So first step is to understand what are your system specification. Second step is you have to find out the converter topology, right? The power electronic converter you have to select. So for example, for a two-wheeler, or three-wheeler, or four-wheeler motor, we need our input is going to be DC, and I need to have an AC motor, three-phase AC motor. So definitely natural choice would be a voltage source inverter. That's what we have studied also, right? So that is what I mean by converter topology. Some other application will need some other converter topology. So based on your requirement, you have to find out what converter topology suits you. Okay. So do note that, of course, I did not discuss all the topologies together, but I did summarize all the topologies for you in a very short document. Let me show you why did I kept that. So if you go to this Power Electronic Basics folder, inside that there is a main study material document. Sorry, looks like there is some connection problem. Hello, am I audible? Any TA available? Can you please confirm, or any participants? Can you please confirm whether you can hear me? You can hear me. Okay. Thank you so much. So I can see there are 2-3 questions. Which type switch used in EV car? That I already addressed. Before closing, please share Google Drive link once again for taking PPT for yesterday and today. Right, no problem. So sorry, there is some Google Drive connection issue. So for all my classes, I am keeping study materials in a single Google Drive. I shared the link multiple times. It is same link for all classes, right? I'll share it once again, no problem. Only issue is the 2-3 minutes are lost in that process. So somehow my Google Drive is a bit slow. It says I'm signed out, but I did not do any logout. Sorry for the delay. I think in 1 or 2 minutes it should be done. In high-end electric vehicles, they use another protection or arrangement in between. They call it distribution box. Okay, but battery is not connected to the motor directly because battery is DC, and most of the motor that we use, these are AC in nature. Okay, so in between we connected DC to AC motor controller. I hope that is clear. I'm very sorry. I don't know why this Google Drive has become so slow. So this link, I'll share it once again. And what I wanted to mention is in the power electronic class, there is one summary document I have made. Let me share it again, which is already available in your study material. So this is the document that I was referring to. Not this one, sorry. It is already uploaded. I'll just show you. Yeah, I don't know why this Google Drive suddenly stopped working. Later on I'll show it. I hope that is okay. So what I wanted to tell is for different power electronic segment, right? Like DC to AC, AC to DC, which are the converters that are popularly used, how their input output are related. All those things are informed in a single short document, and that I gave you so that later on you can refer very easily. All right. So for this particular application, this is your battery, and this is the motor. So in between, I know I have to use a DC to AC converter, right? So that is about topology. So once we are sure about the power circuit topology, around it we have to design so many other components that we already discussed multiple times. For example, to generate gate pulses for the switching devices, we need gate drivers, right? And eventually the gate pulses are generated from the microcontroller, so we need to use a microcontroller. Then we need to use sensor interface circuits. We need to increase several protection circuits, different connections, terminals, communication channels. So all those things you make a list, and then you decide which component to use. Component selection is basically iterative process, right? So based on your first range of requirement, we generally do one list of selections. So when we do these selections, right, do note that, as I told multiple times, that inverter or motor controller is not only about 6 switching devices. It needs so many other supporting things, right? The DC link capacitor, the driver circuit, the microcontroller, then everything has to be done in a PCB. So a list of all those components I have given here. And then eventually what we do, we prepare a bill of material. We call it BOM, bill of material, right? So we make a schematic circuit diagram, okay, how all these components are electrically connected. We use softwares like Altium, someone use Eagle, Orchid. Nowadays, KiCad is also a very popular software. So all this software, what we do, we first make schematic circuit. Okay, then we do PCB layout. So basically how these 6 switching devices are connected, how this will be connected to the battery, how the driver circuit is connected. So all those things we make a circuit diagram. And we give name for the switches, one name for each of the components, right? For example, if I use multiple capacitors, we give them different names, okay? And then we also mention in my reference sheet what are their part values. For example, in some capacitor, I'm using 1000 microfarad. Some capacitor will be only 2 microfarad, 1 microfarad. So which capacitor is what that we relate. And then what is the part number? Let's say I'm using this my capacitor from Mauser or Element 14, so or some manufacturer. So for our reference, we make the part numbers, and also we estimate their price, and from where we are buying the component, right? So all those things we make a preliminary list. How many quantity we need, what are their values, what are their part number, from which site I'm ordering them, right? And what is their cost. So those things we first make a list. So this gives me clarity in the sense how all the components are connected, whether I'm missing anything or not. At the same time, it will also give me an idea about the cost, right? And then its availability also. And this is at the preliminary level. So once you are done with that, now we also do some simulation study. I'm coming to it. Parallelly, we also do thermal study, right? Now, this also I told you earlier that when a switching device is conducting, or it is switching from on to off to on, there will be some losses in the switching device. There are broadly 2 categories of losses: conduction loss and switching loss. Obviously, conduction loss is the loss when the switch is conducting, when it is on, right? And it is carrying some current. And then second loss will be switching loss, when it is transitioning from on to off or off to on, At the time there will be some losses in the switches. So all this loss eventually generate heat in the switches. So those heat you have to take out from the switches, otherwise it may damage the switch, right? So typically you have to do some cooling arrangement. So if your motor controller, there is not very stringent size restrictions, you can use natural cooling or fan based cooling. And if you need a very compact solution, you need liquid cooling, right? For example, if you see the Tesla motor controller, they use liquid cooling. So what they do basically, in the motor controller itself, they will have some channels through which they send cold liquid. And when this liquid goes through the channel, sorry, it gets heated up because there are losses in the switches. So you get heated up. That high temperature or that heated up liquid, you take it out, and then you again in a compressor, you cool it, and again you circulate back. So this kind of thing goes on. And you keep your switching devices within allowable temperature, all right? So now, how do you estimate losses? How do you design this heatsink? These are, again, each topic will take us several hours, right? So some preliminary basic reference I have given you as a video records. So for example, how do you calculate losses in a MOSFET? Then how do you calculate heatsink, right? So that kind of thing, I've given some study material for you if you're interested. So that helps you to design how much heatsink size you need. Heatsink generally we use aluminum. Then you are casing those things. So parallelly, we also decide about the control strategy, right? Ultimately, to control the motor controller, you need to know which motor you are using, what kind of speed control strategy that you have to use. For example, in PMSM, which strategy you are going to use? Field-oriented control, right? That we discussed. So all this you have to decide that I'm using BLDC, I'll go with this control. I'm using induction machine, I'll go with that control. I'm using SRM, it will be separate control together. SRM is a very unique motor, right? Its power circuit is different, its control philosophy is different, it is entirely different. But for induction machine, for synchronous reluctance machine, for BLDC, for PMSM, all of them are using this same structure. Okay, let me write down again. The same DC to AC converter, it will be used in BLDC, it will be used in PMSM, it will be used in SYRM, it will be used for induction machine. So all these four common machines, they are going to use the same inverter. Okay, all of them can be done with same inverter structure. So that's why I spent so much time explaining this inverter. Whereas SRM is a different thing. Switch reluctance motor, it needs a different motor controller, different power electronic converter. Okay. Now, so once you know which motor you are going to use, you decide the speed control strategy, right? Typically for PMSM, BLDC, for PMSM, SORM, these things, we generally use some or other form of field-oriented control. Okay. Whereas for BLDC, we use trapezoidal control. These are the common choices. Okay. So once you have decided the control strategy, what generally we do, we first do the simulation study, right? We don't go ahead with the hardware first. We do this strategy development in a MATLAB or similar software, as I told earlier, right? All this field-oriented strategy, as I mentioned, this we verify in the simulation software first. MATLAB is generally very popular choice for that. So you can also get BLDC motor. In fact, for BLDC motor, I have shared a simulation file with you. If your time permits, you can study that in detail. So once you are happy with this simulation level things, right? Then what we do, we develop a hardware prototype. So in hardware prototype, in the first version, we generally keep it more relaxed. We don't go with the final target shape. Because for the first time when we are developing, we want to debug it easily. If there is any issue, we should be able to find out easily. So we generally make it more relaxed, more spread out in the lab level. For example, here you can see on that image, these are the example of driver circuit. Okay. Then the sensing circuit is there in that green PCB. We used a microcontroller, an advanced version of it, DSP, right? So that how it looks like. It is kept in a box. Then PCB where all components are mounted. Then, for example, these are the heatsink. Okay, so these are some example first level prototype what we do. Okay, because at first level we want to see whether my components selection is okay, whether my control strategy is okay. So with this, we do basic level of prototype development, and then we do a lot of testing around it. Sometimes we, at the first level also, we try to make a compact version. If my previous experience with this particular product is good, for example, let's say we already designed a motor controller for two-wheeler, now we want to design a motor controller for three-wheeler. So I know most of the things, right? So I can easily directly start with the compact version. So then in a motor test bench, for example, since I'm talking about motor controller, I'm showing some of the testing facility that we use to test all this system, right? So here you can see this is a hub motor. This hub motor was designed by our team only. We designed it for around 500 watt and 300 RPM rating. This can be directly fitted into wheel. So once you design this hub motor, you test with different motor controllers. We also have our own motor controller. If time permits, I'll share with you. In fact, this entire setting that you see, these are all in our lab. These two, okay. This is an example where we have a facility we can test up to 100. Actually, we can test more than 100 kilowatt system also. These are all 4-quadrant drive. So we can test motoring operation, we can test regenerative braking, a lot of things we can do. We have test setup of around 30 kilowatt. We have a smaller test bench of 1 kilowatt, 2 kilowatt, that also, right? So we made a different ranges so that all these things can be tested. We have some high-end oscilloscope. We have power analyzer, right? We have torque sensors. So then once we put everything into the system, we test what is the efficiency of this system, how fast they respond, whether they can achieve desired torque, desired speed, right? So all those things we test at the development stage. And once you are done with the first prototype, what we do is you put things on a vehicle, right? For example, here you can see this is one of our VLDC motor. These are designed in-house. This is what that electric three-wheeler or Toto I keep on referring to. So one motor and motor controller for these vehicles, we designed it from scratch, and eventually after level testing, we have kept in, we have fitted into the vehicle for on-road testing. So this is the motor, and this was our motor controller, right? Our motor controller has several advanced features as compared to the motor controller available in market. A video is also there in my YouTube channel. If you're interested, you can check it. So then while you do on-road testing, a lot of data analysis is also important. So what we did, we came up with our own display, our own program display with more information. And at the same time, a lot of information we kept on collecting in a mobile for data record and further analysis, right? So how during on-road testing, whether we achieve regenerative braking and all those things, right? What is the speed, what is the current, etc. So we keep measuring important variables, what we need. And that's how once we're happy, we go into the final version. So first you do test on a lab level. Then what you do is you go to on-road testing, right? And if you're happy, next step is you go for certification. So just for an example, this is our motor controller. We called it motor cum vehicle controller. It was an advanced controller. So we already got Indian patent for it. So this one was this. We already got Indian patent granted now. Because it has several new features which are industry, this category first, right? So this patent was granted. You can see how a patent certificate looks like in case you have not applied earlier. And this is the motor that we designed in-house. Okay, everything was done from scratch, and we have an industry partner in Thane, Mumbai. And then they have fabricated it. And then eventually we took it to ICAT. So this was certified by ICAT. In India, you know, for automotive product, whatever you design, you can approach ARAI, you can go to ICAT for their certification, right? So this particular motor that we had designed, it got two certification. One is for IP67. As I told, IP67 is basically a ingress protection from water and dust. So up to what it can withstand and perform satisfactorily, that certification. Then one certification is for AIS 041. Again, it was ICAT certified for our motor. Then you can see how the certificates looks like. So, you know, sometimes we claim that my motor is 1 kilowatt, my motor is 2 kilowatt, my motor can deliver this much speed, this much torque. But this is what we claim. So these agencies like ARAI, ICAT, they certify whether your claims are correct or not, up to what your product can deliver. So you get a certification of your product, right? With this confident, you can go to the industries, right? And then you can sell your products, or you can, of course, do market level things. So this is how, in a nutshell, what we do for step by step for motor controller designs, right? So let me know if you have any questions. I remember 2-3 questions are from previous classes that I'll take up next. And if time permits, I'll also talk about BLDC a bit. Okay, I can see maybe some of you are having a voice issue. But I think for someone else, it was clear. So there is a question on what work is motor cum vehicle controller, right? So let me give you an, it is basically an Indian patent granted technology for us. I'll show you. Just give me 2 minutes. What is it exactly? I'll discuss. This is a very interesting project that we actually took up earlier, and I take this opportunity to then shortly talk about this particular work. So what is it basically? See, typically in a motor controller, what happens is that you just control the motor. You control torque of the motor, you control speed of the motor, right? And there are some vehicle supervisory level control features that is generally used by a separate controller in high-end electric vehicles. So basically, in high-end vehicles, you have a motor controller which does motor controller things, and there is a vehicle controller, vehicle supervisory controller. Okay, these two are separate products, right? In high-end vehicles. Now, what we did is we combined them together in a single package, small project for e-rickshaw. Now, example of what this vehicle supervisory controller. Of course, we did not implement all fancy features of vehicle supervisory controller. That will make the system very costly, right? So we selected few interesting, important features of the vehicle supervisory controller, and we embedded into the motor controller itself. Okay. So, for example, range estimation. In electric rickshaw, if you see nowadays, they don't tell you how many kilometers you will be able to drive with the remaining charge of the battery, right? So we provided that for the first time, approximately how much range is remaining, and we also showed it in the display, right? If time permits, I'll show you. Then another feature we added, these are all vehicle supervisory controller feature, is that sometimes what happens is that, you know, in this kind of vehicle, sometimes people do overload. It is actually designed for, let's say, 4 passengers and 1 driver, but they keep on having more people. And then these vehicles, what happens is these are designed for certain gradability, but sometimes people try to extend, they try to go higher slopes, right? So what happens is that if you do not protect your motor and motor controller, due to this overloading, it can damage, right? So a protection we incorporated in our system. How? See, when you're overloading your motor and motor controller, what happens is that due to those higher current and all, temperature of the motor or motor controller goes up, right? So we had temperature controller or temperature sensor kept in motor and motor controller both. So these are very low cost sensors, not very expensive.